This is the second video discussing hypothesis testing, the material from Chapter 9. We're to continue with our discussion from the last video and jump into two additional examples. The first example will be exactly like the example we covered in the last video, except I'm going to make it a two-tailed test rather than a one-tailed test. In the previous video, we looked at a right-tailed test, but now we'll look at a different null and alternative hypothesis. So the null hypothesis for a two-tailed test will be stated with an equality. So again, we're dealing with IQ scores, so the null hypothesis will be that IQ is equal to 100. And the alternative hypothesis will simply be the opposite of that, which is that mean IQ scores in the population are not equal to 100. Again, we specify the level of significance. Alpha is equal to 10%. The only thing that I will mention right now is that alpha being equal to 10% means that there's area left over in both tails, since it's a two-tailed distribution, with 5% left in each tail, for a total of 10%. So the area that's left in each one of these tails of the sampling distribution of the test statistic is actually alpha over 2. In our case, that'll be 5%. We collect sample data again, we calculate our point estimate and standard error, and nothing here has changed from the last example. 150 IQ tests are administered, the sample average is 108. The standard deviation is estimated to be 38 points. That 38-point standard deviation is used in order to calculate the standard error of the estimate, which once again is equal to 3.1. Step 4 is to calculate the test statistic, and the calculation of the test statistic hasn't changed. We're concerned with the distribution of the test statistic when the null hypothesis holds with equality. So we'll take our sample data and we'll calculate X bar. That's our sample information. We're comparing that to our null hypothesis when it holds with equality, and our null hypothesis in this case is actually stated with an equality, and it is that IQ tests in the population have an average of 100. So we have the difference between 108 and 100, and the question is that difference big enough to reject the null, that using the sample evidence that the population mean is equal to 100. We have to express that in terms of standard deviations, of course, by dividing by the standard error of the estimate. So we still have 2.58 as the value of our test statistic. The only thing that I'll mention here is that in this case, before, when we had a right-tailed test, it was a large t-statistic that provided evidence against the null hypothesis. So our rejection region was out to the right tail of the distribution of the test statistic. But now we have a two-tailed test. So it's still true that a large value of the test statistic will provide evidence against the null. But because of the way the null is stated and the alternative hypothesis is stated, such that it's two-tailed, a very small value of the test statistic, it will be a negative value. So a really negative value of the test statistic will place us out here in a rejection region that's in the lower tail. So we have to concern ourselves with both tails. Next, we will determine if the null hypothesis is rejected or not. And again, there are two equivalent approaches. We can use the p-value approach, or we can use the critical value method. We'll start with the p-value method. So when we have a two-tailed test, there are basically two possibilities. When we calculate the value of the test statistic, we could come up with a positive test statistic. That means that our sample evidence provides evidence of a mean that's to the right of the hypothesized value. That's one possibility, and so we may end up with a value of our t-statistic that's positive. Maybe it's right here. Here's our positive t-statistic. In that case, what we would do is we would look at the area that's to the right of that t-statistic, but that's only 1/2 of the p-value, because we actually have minus t, and we have to account for both tails of the distribution. So we would take the value that we find in the table for the p-value in the area that's left to the right of the positive t statistic, we would find that area and we'd have to double it to get the p-value. Of course, the other possibility is that we calculate the test statistic and it turns out to be negative. Typically, then we might look for the area that's back here to the left of the minus t value. And once again, that's only 1/2 of the p-value, so we would have to double it in order to get the p-value. So once we have the p-value, we will compare it to our significance level, and once again, if it's smaller than our significance level, we reject the null hypothesis. I'll show you a picture of this in just a second. But the p-value that we calculated in our right tail test was 0.005. You may recall that that was the area that's to the right of the value of our test statistic. We looked that value up in a t-table. In this case, we have to account for both tails, so I double it to get my p-value. So the answer is 0.01. That's my p-value. Since 0.01 is less than 0.1, 1% is less than 10%, I will reject the null hypothesis. Here's a picture. What I'm doing is I'm looking at the area that's to the right of my test statistic, value of my test statistic, which we know is 2.58, and that's 0.005. But remember that I have minus 2.58 over here in the left tail, and the area that is to the left of minus 2.58 is also 0.005. So the total p-value is equal to 0.005 on the left plus the 0.005 on the right for a total of 0.01. So that's my actual p-value. And I'm comparing that p-value, which is these two red shaded areas that I have I just colored in, I'm comparing that to the significance level, which is represented by the total of these two areas in the right tail and in the left tail with 5% of the area in each. So alpha over 2 is 0.05 on the right, and alpha over 2 is 0.05 on the right, for a total alpha equal to 0.1, or a 10% significance level. Okay, so we can also use the critical value approach. To use the critical value approach, which is equivalent, all we have to do is calculate T alpha over 2 and compare it to T. Now again, there are two cases. If T is positive, we're going to compare T to T alpha over 2. There will be two different critical values, one in the lower tail and one in the upper tail. And if T is positive, we're going to compare our test statistic T to the positive value T alpha over 2. Then we will reject the null hypothesis if T is greater than or equal to T alpha over 2. If we end up with a test statistic that's negative, we'll compare it to minus T alpha over 2, and if it's smaller than minus T alpha over 2, we will reject the null hypothesis. I'll draw you a picture in just a second, but when I go to a t-table, you should know how to do this by now, and you look up T alpha over 2, alpha is equal to 0.1, so T alpha over 2 is 0.05. When I look up T 0.05 for a T distribution with 149 degrees of freedom, right here, 149 degrees of freedom, I looked this up on the computer actually, you get 1.66 is the answer. But we have to recognize there are actually two different critical values. You're supposed to know that there's 1.66 on the right. I'm going to use that if I get a positive value for my test statistic. And there's also minus 1.66 on the left, which will be what I'll compare my test statistic to if my test statistic turns out to be negative. Now in this case, of course, we know that my test statistic turned out to be positive. So comparing that to the positive critical value, I see that it's greater than the positive critical value, and therefore, according to my rule, I reject the null hypothesis. And again, here's a picture. It's the same picture. What I've done is I've determined the value of the critical value at 5%. It's alpha over 2 at 5%. So there's 5% of the area left in this tail. And then this is another critical value that I have to concern myself with, minus 1.66. That's back here in the left-hand tail. So once I've determined that 1.66 and minus 1.66 are my two critical values, I calculate the value of the test statistic, which is 2.58. I note that 2.58 is positive, so the appropriate comparison is between the 2.58 and the positive critical value, 1.66. Since 2.58 is greater than 1.66, I'm in the rejection region, and I reject the null hypothesis. If my test statistic had turned out to be negative, right, like minus 2.58 instead of 2.58, or minus anything, I would end up taking that test statistic and comparing it to minus 1.66. And if it were smaller than minus 1.66, I would reject the null hypothesis. The last example I'm going to work through with you is going to be a left tail test. We haven't seen one of those yet. And I'm also going to work through the example for a population proportion. It's very similar to what we've done for the mean, but there are basically two small changes I'll point out here. First, I'm going to use the normal approximation to the binomial distribution. So you should know the conditions under which we can do that. I'm going to assume that those hold. So you'll see z-scores here. My test statistic will be labeled z. And the calculation of the test statistic will use a different formula simply because we have a different point estimator that we're testing. We're testing a hypothesis about a different population parameter. The point estimator has is different, and the formula for the standard error of the estimate is different. But the basic idea is still the same. Okay, the approach hasn't really changed. So I need to come up with a different example that's appropriate for proportions. Let's say we have an example where there's a school district that has a test that they administer. It's a standardized test. And the school district needs to have 70% of their students pass this test, or the school will be labeled as a failing school district. And so we sample 200 tests, and we compute a sample proportion of students who pass the test. And we find that that sample proportion, p bar, is equal to 0.68, which is below the 70% benchmark. But of course we know, as statisticians, that we wouldn't expect to get the exact population proportion when we sample. Sometimes we'll undershoot it, maybe get something like 68%. Sometimes we might overshoot it and get 72%, etc. And the question is this 2-point difference enough to conclude that the school district is not meeting the standards? This is a perfect case for a hypothesis test using a left-tailed test. So when I state my null hypothesis, which is always step one, I'm going to give the school district the benefit of the doubt. My null hypothesis is going to be that the population proportion of students passing the test is equal to the benchmark or greater. So I'm going to require a good amount of evidence against this null hypothesis before I conclude that the sample evidence is more consistent with the alternative, which is that the school district is failing their students and less than 70% of the students are passing. Now, I think that there's some risk, additional risk here in making a type 1 error in concluding that the school district is not meeting the standards when in fact they are. And so I'm going to pick a level of significance that's equal to 5% instead of 10%. So I'm only willing to take a 5% risk of making a type 1 error and concluding that the school district isn't performing well when in fact they are. So I control that by picking my alpha, and then I collect my sample data and calculate the point estimate and the standard error of the estimate. So I have 200 tests, and we said that the sample proportion was 0.68, and then we calculate the standard error of the estimate, which I covered for the sample proportion when we talked about sampling distributions. So I'm not going to go over that formula again here. You should be familiar with it. If you don't remember, go and look it up in your textbook or watch that video again. The only thing I will point out here is that when I calculate the standard error of the estimate, it's the 0.7, the value of p under the null hypothesis when the null hypothesis holds for the quality that belongs in the calculation of the standard error of the estimate, not the 0.68. And that's because we're concerned with the distribution of the test statistic when the null hypothesis holds. So we put the 0.7 in there, not the 0.68. You can see that in this formula, where it's the hypothesized value of P naught that belongs in the calculation of the standard error of the estimate. So once again, we've got 0.68 minus 0.7. That's our 2-point difference between our sample evidence and our null hypothesis when it holds with equality. And I don't want the raw difference, I want to standardize that. So I divide by 0.032, which is the standard error of the estimate. So what I find is that I'm 0.625 standard deviations below the hypothesized value of 0.7. The question is that far enough below to reject the null hypothesis? So we'll determine that by using the p-value approach or the critical value method, one or the other. So the area under the standard normal distribution to the left of the value of the test statistic this time is the p-value. So we've looked at calculating p-values in a couple of different ways. We looked at it as the area that's to the right of the test statistic for a right-tailed test. We looked at it as the area that's to the right or left of the test statistic, depending on whether the test statistic is positive or negative, in a two-tailed test, but we had to remember to take that value and multiply it by 2. And now in this case, we're going to look at the p-value, because it's a left-tailed test. We're going to look at it as the area that's left over to the left only of our test statistic. So we have the value of our test statistic, t, or I guess in this case we're using z. So our test statistic is z, and we're going to look at the area that's to the left because it's a left-tailed test. So we compare the p-value, of course, to the level of significance, and if it's smaller than the level of significance, we'll reject the null hypothesis. It's the same rule that we've been using in the other two cases. So I'll draw you a picture in a moment, but the calculation is as follows. If I looked up the p-value that was associated with the value of our test statistic, which we calculated on the previous slide, and I found out that that was equal to 0.27. So at the value of our test statistic, right, this area to the left of the value of our test statistic was equal to 0.27. 0.27 is greater than 0.05, so by our rule we fail to reject the null hypothesis. There doesn't seem to be enough evidence against the school district if we're only willing to make a 5%, accept a 5% probability of making a type 1 error. And here's a picture. So the value of our test statistic left, an area to the left, which was equal to 0.27. The value of that test statistic, which I forgot going back here, was minus 0.625. So minus 0.625 is here, 625, with 0.27 of the area left here, to the left of it, 0.27. So that's our p-value, which is clearly greater than the 5%. I picked the 5% significance level. You can also use the critical value approach. Here we have to find z alpha. You can look that up in a table or use a formula in Excel or some other software package to find the value of z for which 5% of the area is left to the left of z, not to the right of z, but to the left of z. So whatever table you're using, excuse me, or formula in a software package, make sure you're using it correctly. Then we will compare z to z alpha, and if z is smaller than minus z alpha, then we'll reject the null hypothesis. My convention here is that I've looked up z alpha. This is based on a formula that I used in Excel, and z alpha is positive. So you have to remember that we should end up with a negative critical value because we have a left-tailed test. So if you get lost, draw a picture. But when I looked up z alpha, when I looked up in a table the value of z, I actually, because it's a symmetric distribution, I used a table that just tabulated the right-hand side of the standard normal distribution. I found the value of z for which 5% was left to the right of that value, That's not really what I want, though. I want to have the value of z with this 5% left to the left of the value. But because the distribution is symmetric, I could take the 1.64 that I looked up in the table and just multiply it by -1. So my critical value here is minus 1.64. The value of my test statistic was minus 0.625. Since minus 0.625 is greater than minus 1.64, once again, not surprisingly, I failed to reject the null hypothesis. And again, it's the same picture, except here I'm looking at the critical value, right? And I'm looking at the value of my test statistic, which is minus 0.625. Minus 0.625 is out here somewhere. That's the value of my test statistic. And it doesn't make it into this rejection region, right? So here I'm comparing with the critical value approach, the value of 0.625, the value of my test statistic, to my critical value that I've looked up in a table, minus 1.64. So I have an opportunity for you to work through a hypothesis test using a unique data set. I would like you to open up Chapter 8 worksheet for video lecture checkpoints, which is available on Moodle, and answer a couple of questions to make sure that you followed along and you know how to complete these hypothesis tests.